Okay. Okay. Today I'm gonna talk about how how we connect the PLC Open motion control with the MoveIt2 and how we run it on the Intel Edge control for industrial platform, and our motivation to do this work, and also a little introduction to the Intel Edge control for industrial platform. For the first motivation, we do this work is that we want to put MoveIt2 into the robot native controller. I think this figure demonstrates a common usage scenario that users to use MoveIt2. When user use MoveIt2, it usually will install MoveIt2 into IPC with Ubuntu on the IPC, and connect this IPC to robot native controller, which runs real-time operating system like VSWorks or QNX. But with this current usage model, that we found that there is some problem. The first problem that if runs in the MoveIt2 on the Ubuntu, that there is no real-time guarantees that to the movie. That means if a movie runs some real-time tasks, there is no time determinant guarantee from the system. And the second problem is that usually, actually, for the real-time workload, it only needs one core of the CPU to run the real-time workload. So actually, there is a lot of computing power that is wasted by using two computer machines. So if one computer can do all the work, while we need two machines. So another problem is that there is no guarantees to the communication between the two machines. That means the communication latency between the two machines, there is no mechanism to guarantee them, because a lot of factors can influence this communication latency, and it could be very random. And if there is some safety work need to run on the IPC controller, usually it needs some time synchronization between the two machines. But with the most common native robot controller in the market, with their exposed interface, it is not possible to accomplish this real-time guarantee and time synchronization, except using the TSN technique. But if using the TSN technique, it will bring in much more cost into the system. And another problem is that we think for when we connect MoveIt to different robot arms, we always need to create a robot arm, ROS2 driver for that robot arm with based on the manufacturer exposed Ethernet interface. But if MoveIt can connect directly to the servo motors, because the servo motors usually follows the industrial standards. then it would be easy for MoveIt to adapt to different roped arms. So that's the motive. Our first motivation that to put MoveIt2 into a native controller. And for the second motivation is that we want to connect the PLC open motion control to the MoveIt2. The reason is that we found that in the industrial market that actually PLC open motion control has this standard has been widely accepted by the manufacturer and the players in the industrial control market. And for most our industrial control customers, actually they have very wide products that cover the servo motors, the CNC machines, and the PLC motion control machines, and always this kind of control market players. They also want to have their own roped arm products instead of buying the roped arm from a third party to reduce their cost and to make their integration easier. So they want to reuse their software components that has been used in the in the control of other machines to be used in their roped arm products. And also, I think when these kind of customers to build their roped arm products, they also need MoveIt2 to reduce their development work, because PLC Open has a Part 4. PLC Open Motion Control has a Part 4 standard that covers multi-axis motion planning. But many parts of this standard actually are covered by some functions of MoveIt2, including the kinematics and the path interpolation. So that's the reason that we want to connect the PLC open motion control to the MoveIt2. So here, this slide demonstrates the software components that we talked about, how to connect the PLC open motion control to the MoveIt2. And these components are all running on the Intel edge control for industrial platform. So beyond the Intel hardware that's in the CPU, we're running the real-time Linux-based real-time operating system, which is the PrimRT or the Xenomai. And beyond the real-time operating system, it's industrial field bus master stack component that following the industrial EtherCAT and the CAN open standard. And then there is a software components named SAL. That means a servo abstraction layer that will bridge the industrial field bus to PLC open motion control library that we call it ATimotion. The ATimotion following the PLC open motion standard that and provides some standard software function blocks that running on the joint motor level, make the motion planning for the joint model, joint motor, and with also some function block scheduling algorithm. And this library can be loaded and programmed in some soft PLC software. And in this soft PLC software, the on-site factory engineer can program the joint level motion by their familiar PLC language. And actually, the PLC Open Motion Library can also be called by their C++ interface. All the components that on the left side of the dashed line actually are running on the real-time domain. And in our current design that we run the MoveIt2 on the non-real-time domain, and we connect the real-time PLC open motion control with the MoveIt2 by the shared memory rim buffer tag. And all the real-time and the non-real-time workloads are running on the on one CPU to accomplish the motion planning task. So in this slide, I'm gonna introduce a little bit of the edge control for Intel edge control for the industrial platform. In the last slide, we all the component in the last slide is open source components, but actually they are not easily connected and put together. Actually, many of them has been optimized and tuned by the edge control for industrial platform to guarantee the best performance of real-time on the Intel hardware. So the target of this platform is to try to make any kind of industrial PC if it installs the edge control for industrial, it can become a real-time performance guaranteed industrial controller. So actually, it provides a lot of tools to help the user to do that. Because for tuning the real-time performance, there are a lot of steps that need to do not only in Linux kernel, but also in the BIOS firmware, and also in some in the hypervisor software. So the ECI provides some tools to help user automatically to check the configurations and tune the configuration to reduce the message transmit latency in the system, and also guarantee there is no interference to disturb the real-time performance, and also provide some motion control application samples for the user to reference. And on this slide, we demonstrate the proof of concept of how we connect the PLC open motion to the MoveIt2 you can see that we use the PLC. We run the PLC open motion control to drive each joint motors of this six axis root arm, and the communication of each motor is CAN bus based, and we isolated one core of the CPU dedicated for the real-time workload, and left the other three core of the CPU to MoveIt2 to do the trajectory motion planning, and the output of the MoveIt2 trajectory will be sent to the PLC open program through the shared memory, and the joint rotor state will feedback from the real-time domain to the rows system, also from the shared memory. Okay, you can see that right now we only need one IPC to do all the control stuff. And one of our another current work is copy this framework to run on the Windows. So for on the Windows, we use the in-time real-time system, which can isolate the one real-time kernel to run the real-time workloads. Here, the PLC open workload will run in this isolated real-time kernel by in time, and for the and the MoveIt2 will run within the Windows, and this work we will drive a 6-axis EtherCAT based root arm, and this is one of our current work still in progress. Yeah. And another work of our work is that we challenge the system further, that by integrating the machine vision workloads into the system, that we try to run the real-time workloads, move to motion planning and machine vision workloads together in one IPC. So there will be one core of the CPU that dedicated for the real-time workloads, and three core of the CPU used by MoveIt2 to run the motion planning, and the vision workload will be offloaded to the integrated GPU that can be accelerated by Intel OpenVINO and DPC++ tools. And another work of our team is that we also try to do a new kind of controller for the mobile manipulator, that by integrating the AMR control the roped arm control together, running parallel on the on one system. So for this task, we will use the Acron hypervisor that provided by ECI to do that. The Acron hypervisor will visualize the two real-time virtual machines that will holding the AMR control workloads and also the roped arm workloads together. Yeah, and this is another work that we are planning to do in this year. Yeah.
All right. Thank you so much.
Yeah.
Presentation. This looks amazing. Yeah, you can stop sharing your screen probably at this point. There's no time for questions, I think. But I think what would be great if you could post links in the chat for web pages about the open source aspects of what you just presented. I think people are very interested in that. I also saw that you use the Jaka arm. If you have any open source MoveIt configs drivers for that, I think that would be great to share. There's a lot that you presented today that I think people want to learn more about. So whatever you can share, please post information in the chat.
Yeah.
Okay.